In this video, we will demonstrate how to match an experimental powder X-ray diffraction pattern to a simulated pattern derived from a known crystal structure. To begin, open Mercury. To simulate a powder pattern, it is necessary to have either a CSD structure selected or to open a structure file with atomic coordinates and unit cell information, such as a CIF. The example we will use is a polymorph of paracetamol. To load the CSD entries for paracetamol, type HXACAN in the Structure Navigator. This will display the first entry in the RefCode family, the other members of the RefCode family being indicated by the additional numerical characters. Press the Powder button in the Display Options toolbar. Alternatively, you can access the powder pattern simulation from the Calculate menu at the top. The simulated powder pattern for the current structure is displayed in the window. For an introduction to the simulator, see the video linked in the description and shown at the end of this video. Underneath the current structure drop-down menu, you will see buttons to control the display. You can toggle off and on the display of the simulated pattern, select a reference and choose whether to display it, and run a pattern optimization and choose whether to display the resulting pattern. To load a reference structure, click the Reference button. In the File Explorer, select a diffraction pattern in one of the permitted formats. Note that for pattern optimization, a background correction should be applied to the reference data. Suggestions for applying background correction are given in the video description. As we can see, the simulated pattern derived from CSD entry HXACAN is a poor match for the experimental pattern. This is also indicated by the similarity score, which is 0.0991. The similarity score goes from 0 for no match to 1 for the perfect match as defined by the cross-correlation method of de Gelder et al. See the article linked in the description for further information. If we choose HXACAN01 in the Structure Navigator, it is clearly a better match in terms of peak position. However, there are substantial differences in peak intensity. The simulation can be optimized to see if there is a better potential match using the Optimize feature. Optimization is carried out using AutoFidel, Jonas Neumann's implementation of the Fidel method described in the article linked in the description. Before running the optimization, we will check the settings. The settings can be accessed by clicking Customize, and then from the dialog clicking on the Match Optimizer tab. Here, the optimizer settings can be varied. The settings include tolerances on the unit cell angles and lengths, and the maximum 2θ angle to be used in optimization. Generally, it is not recommended to increase the limit beyond 35 degrees, as this is typically a fingerprint region, which the optimizer can struggle with. The cell optimization can also be disabled if you do not wish to include it. The Optimize Molecule menu allows for the position and orientation of the molecule in the unit cell to be changed by choosing the Position option. The Geometry option also optimizes position and orientation, but additionally allows internal torsion angles to be optimized. The Optimize Preferred Orientation menu gives a variety of options for accounting for preferred orientation. BFDH uses the simulated BFDH morphology to predict a preferred orientation with an optimizable March delays parameter. Free is a fully optimizable preferred orientation, whereas Search is a brute force search to find the preferred orientation with an optimizable March delays parameter. In this example, we will use the default values for the unit cell tolerances and maximum 2θ of 30 degrees, since there are no peaks above this value in the reference pattern. We will also optimize the molecule using the geometry option and the preferred orientation using the free method. Click Apply, then in the main simulation window, click Optimize and wait for the calculation to finish. Once the calculation has finished, a summary table appears in a new window showing changes to the parameters which have been optimized. In this case, you can see that small changes have been made to the unit cell parameters and that the 101 Miller plane has been identified as the preferred orientation with an optimized march delays parameter of 1.177. In the main simulation window, you will now see two similarity scores, one for the original pattern and the other for the optimized one. There has been a modest improvement after optimization. Note that a score of 0.8 or above is indicative of a possible match, so this pattern is worth investigating. Other entries in the HXACAN refcode family might provide a better score. If the display is not very clear, you can change the color and line style for the traces from the Display tab of the powder pattern settings. You may also wish to offset the patterns vertically using the Y-axis offset option in the reference pattern area. Click Apply to make sure your changes take effect. If you want to save the simulations, either optimized or unoptimized, you can choose to do so by clicking on the Save button and selecting the option you want. If you would like to explore pattern matching and optimization programmatically, for example to compare multiple experimental and simulated patterns with one another, this can be done with the CSD Python API. See the links in the description for more information. We hope that you found this video helpful for your work. Thank you for watching, and don't forget to subscribe to our YouTube channel.